This video is about how to evaluate limits analytically. Everything's great if you have a graph. If I want to evaluate, what height is this function approaching as x approaches c, I could very simply look at the graph. But what if I don't have the graph and I don't know what the function looks like? So we have to look at it a different way. Well, there's a theorem that says that if you have two functions that match at every single point except for one, let's say at c it doesn't match, but the limit exists for one of those functions, it exists for the other and it's the same value. So let's say that the limit for this function that we have here as x approaches c is L. So the graph comes into a height of L for both sides. Well, there's some other function out there that I could maybe make that matches it for for every point, so it's the same exact graph everywhere except at c. But for this one, I'm going to fill in the hole. Well, if I can figure out what that function is, the one that I'm using in red, then I'll know what height I need for my original function that had the hole, because this hole that's being filled is the answer to the limit for both functions. So what we're going to do is we're going to start with some kind of function that might have a removable discontinuity, and we're going to remove the discontinuity and evaluate the new function. It's going to be the function that has the hole filled in. So our very first example is, what if you're taking the limit as x approaches 1 of x cubed minus 1 over x minus 1? First rule is that whenever you're doing a limit, the very first thing you should actually do is plug this value into your function and see what happens. So I have 1 cubed minus 1 is 0, and then 1 minus 1 is 0. So evaluating at 1 gives me 0 over 0, and I know that I have a removable discontinuity. Now, this actually tells me more than that. It tells me where that discontinuity is. It's actually happening at 1. Now what that means is that 1 is a 0 for both x cubed minus 1 and for x minus 1. Remember that zeros go with factors. If 1 is a 0, then x minus 1 is a factor. For example, if we have a quadratic and I said x equals 2 and 3 are zeros, so they are x-intercepts, then I know that that function has to have the factors x minus 2 and x minus 3 in it, because if x equals 2, 2 minus 2 is 0, 0 times x minus 3 is 0. That creates a 0. So there is a relationship between the zeros and the factors. Since 1 is a 0 of both of these, I know that x minus 1 is a factor of both of these. And the way we're going to remove the discontinuity is to actually cancel the common factor. So let's say for just a minute that maybe you don't remember how to factor x cubed minus 1. It really doesn't matter, because if you can recognize that 1 is a 0, you already know what one factor is. So I know that x cubed minus 1 is x minus 1 times some other factor. And I already know that x minus 1 is a factor because it's the only thing on the bottom. So I have an x minus 1. If I can figure out my second factor, then I will be able to cancel these out, and I'll look at this function. So we're going to do the limit as x approaches 1 of this. Now to find the second factor, if you don't remember how to factor x cubed minus 1, one thing you can try is long division. So I'm going to do that. I have x cubed minus 1, and I'm going to divide by my common factor, which will be x minus 1. And that should leave me with my other factor. If this truly is a factor, I should get a remainder of 0. Okay, now the way you do long division, it's probably been a while, is you look at your terms with the highest power, so x cubed and x. The question is, how many times does x go into x cubed? Or rather, what do I multiply x by to get x cubed? Well, that's an x squared. So I'm going to write the x squared on the top. And if you remember from the long division algorithm, after you figure out this, you take this, whatever it is, your quotient, and you multiply here. I'm going to have to distribute. So x squared times x is x cubed. X squared times the negative 1 is a negative x squared. After you multiply down, you would draw a line and you would subtract. So since I'm subtracting, I'm going to change the signs here. My x cubes cancel out, And then I'm going to write these in order from highest power to lowest. So the x squared, well, it's an x squared, and this is like an x to the 0 because there is no x sitting there. This is a positive x squared, and then I'm going to bring the minus 1 down. Now I look at my highest power, the terms with the highest power again. X times what is x squared, and that's just a positive x. So I'll put a plus x up here. Once I have something up here, I'm going to multiply it down and again distribute. So x times x is x squared. X times a negative 1 is a negative x. After you multiply, you subtract, which means changing the signs and adding them up. The x squareds cancel out, and I have a positive x and a negative 1. And if you look, they're the exact same thing. So what do I multiply x minus 1 by to get x minus 1? A positive 1. So from this, and since it's the same thing, I know my remainder is going to be 0. This is my other factor. So x squared plus x plus 1. Now it's important to note that I've changed nothing so far. This expression and this expression are equivalent. They both have a removable discontinuity at 1. But if you look at how this one is written, I can cancel out the common factor, and what I've just done is remove the discontinuity. So this is my second graph, the one with the hole filled in. It's x squared plus x plus 1. If I evaluate this limit, it will give me the same exact value as that limit. This just has the hole filled in. So I will take my 1 and I'll plug it in, evaluate the limit, so it's 1 squared plus 1 plus 1, and this limit is 3. Looking at a simpler factoring example, imagine that we're taking the limit as x approaches 2. First thing again is actually to plug in. So 2 minus 2 is 0. 2 squared minus 4 is 4 minus 4 is 0. So I know a couple of things. Since it's 0 over 0, I have a removable discontinuity. I also already know my common factor. Since 2 created the 0 over 0, then I know 2 is a 0 of both of these, and I know that my common factor will be x minus 2. Now this one's really close. So I'm actually going to try to change this one into that. So this is where the algebra comes in. Notice the x is first. So I'm going to move this x into the front. So I'm going to have a negative x plus 2 in my numerator. Everything's fine, but the signs are off. I have a negative x here, a positive x here, a positive 2, and negative 2. So what I'm going to do is actually factor out a negative 1, or just a negative, and this will be x minus 2. So looking at this, if I distribute it back in, I have a negative x, which is right, and a positive 2, which is right. So this is the numerator I actually needed. So this will be the limit as x approaches 2, and then in my numerator I have negative x minus 2. In my denominator, I'm just factoring. Now, I know that how to factor x squared minus 4, but let's just take, just for a second that I didn't. I know my common factor is x minus 2, and I know that I multiply first times first to get that x squared, so this has to be an x, and I have to multiply last times last to get the negative 4. So negative 2 times a positive 2 is negative 4, and then you can check your middle terms, a negative 2x and a positive 2x. So these are the factors of x squared minus 4. And of course, you only go through that process if you don't remember. These are conjugate binomials. The middle terms always cancel out. And if you look, this is the same exact expression as that, just in factored form. This one has a removable discontinuity. If I cancel out my common factor, I know that this is going to equal the limit as x approaches 2. And I still have a negative, so a negative 1 in the numerator and an x plus 2 in the denominator. This does not have a discontinuity at 2, so I can just take my 2 and evaluate the limit, and this limit is a negative 1/4. For this last example, if I plug in 1, I'm going to get 1 plus 1 minus 2, which equals 0, and then 1 squared is 1 minus 1, 0. So again, I have a removable discontinuity, which means I have a common factor, and I already know what it is. If 1 is a 0 of both, then x minus 1 is a factor of both. So I know this is the limit as x approaches 1, and I'm just going to put my common factors on. And again, if you're really good at factoring, you can just factor it and you'll see the common factor. Okay, and I know there will be a second factor for each one. In my numerator, I look at my negative 1. What do you multiply negative 1 by to get a negative 2? And that will be a positive 2. And x times x is x squared. I can check it. X times x, x squared, and negative 1x plus 2x is 1x, and then negative 1 times 2 is a negative 2. In my denominator, x minus 1, and again, these will be conjugate binomials. There is no middle term, but a negative 1 times a positive 1 will give me a negative 1, and then x times x will give me the x squared. The middle two terms cancel out. And now I can actually cancel my common factor and say that this is equal to the limit as x approaches 1 of x plus 2 over x plus 1. There's no longer a discontinuity, and I can just evaluate my limit. So 1 plus 2 is 3. 1 plus 1 is 2. And the answer to the limit is 3/2.